Good morning, everyone. Can you hear me? Yeah. Good morning, and everyone. I am Nisha Agrawal, the coordinator of this workshop. So, first and foremost, I want to extend my gratitude to each one of you for taking the time to join us. Today, your presence here reflects your commitment to learning and growth, and I have no doubt that together we will make this workshop an enriching and a rewarding experience. Now, let me give you a brief overview of what we have planned for today. Our workshop is divided into theoretical and practical sessions. Each session will be interactive and engaging with opportunities for question, discussion, and hands-on activities. And we are starting with the introduction. An introduction where we will explore LITESOPH key concepts. During the demonstration, we will learn the uses of the LITESOPH with some test input datasets. During the hands-on session, to reinforce learning and practical use of the LITESOPH, we will engage you in the hands-on case studies. This activity will allow you to gain hands-on experience with LITESOPH and in turn may be useful for your research or the project work or further development of the LITESOPH. Then we'll have the 30 minutes of question answer and feedback session where we expect your active participation is the key to the success of this workshop. We encourage you to ask questions, seek clarification, and share your insight throughout the day. We have also set aside time for the dedicated question answer and welcome your feedback at the end of the workshop to help us improve for future session. In the conclusion and next step, as we near the end of our time together, we will recap the key takeaways from the workshop and discuss next steps, whether it's applying what you have learned in your professional life, continuing your learning journey, and staying connected with fellow participants. So let me introduce you the key speaker of today's workshop, Professor Vardarajan Srinivasan. Professor Srinivasan obtained his BSc in chemistry from University of Madras in 1998 and MSc chemistry from Indian Institute of Science, Bangalore in 2001. He moved to Princeton University for his PhD on ab initio molecular dynamics, studies of ferroelectric phase transition with Professor Roberto Carr, obtaining the degree in 2006. Subsequently, he worked as a postdoctoral scholar at University of California, Berkeley and Massachusetts Institute of Technology before joining ISR Bhopal as an assistant professor in chemistry in 2010. Currently, he is a professor at same institute. His group focuses on computational approaches to material science problems including magnetism, ferroelectricity, pressure-induced phenomena in materials, and light-matter interaction relevant to chemistry, physics, and biology. Before starting the session, let me walk you through the materials and computational chemistry support web page. So this is a web page created by CDAC Materials and Computational Chemistry Support Group. So under this, we have all the 5 software which are developed under NSM in the area of materials and computational chemistry. So all the information is available onto this web page. So this is a summary page. So you have the list of software. The link. This link will give you the short description and the further detailed description of each of the software is available in this section. And we have the link for these are the list of softwares available for your download and installation on your local system as well. These are the software also available of NSM HPC systems. On few system it is available, and in some time it will be available in all the NSM HPC systems. If you would like to run this software with some data set, input data set, test data sets are available on this link. Whatever training we are organizing, the training material will be available under this YouTube channel. So for our past workshop on AMD Kit software, the videos are available. If any one of you are interested, you can watch this AMD Kit tutorial sessions. We also have this support system available for these applications. So you can put up your queries, ask question in this discussion forum. And other ways for getting the help, you can write us an email or create a ticket for your any issues if you are facing any of these software. We have this discussion forum available for each one of the software, AMD Kit, LITESOPH. So all the you can discuss within the community of materials and computational chemistry. You can post your queries, doubts, seek if you want to seek some help on this some topic, you can put and you can join this forum and you can discuss with the community members. These are the ticketing system for any, if you are looking for any kind of a support, if you are facing any issues with this with the software, you can raise and create a ticket, raise your issues. We have this mailing list as well. So just subscribe to that mailing list. You will get you will connect it to the users community of material science and computational chemistry, and you can post your queries. You can mail us in this mailing list, and all the updates or any changes in the software you will receive through this email mailing list only. So I request all the members of this workshop to kindly subscribe the mailing list of LITESOPH. Then this is the download page where you can find all the downloads are available. So this is just a quick overview of the support page which we have created for MSCC applications. So under one, this is all the information is available under one umbrella of this web page. So in closing, I want to emphasize that this workshop is not just about acquiring the knowledge. It's about building community, bringing like-minded people together, further development and transformation in the area of materials and computational chemistry. And I hope that you will leave here today feeling inspired, energized, and equipped with valuable insight and skills that you can apply in your studies and professional endeavors. Once again, thank you for being here, and let's make this workshop an unforgettable experience. So unfortunately, Professor Vardarajan is not physically available during this workshop. So he shared the recorded video for the concept of LITESOPH. So we are, but the developer teams is available with us. So if you have any queries, you can ask after this video. So we are just playing his recorded video for the concept of LITESOPH. Thank you.
Good morning, everyone, and welcome. Good morning, everyone, and welcome to this MSCC workshop on LITESOPH, Layer Integrated Toolkit and Engine for Simulation of Photo-Induced Phenomena. I'm Varatharajan Srinivasan, and at the outset, let me thank the CDAC team for conducting this workshop. And also, I would like to apologize for not being here because of a conflict with my travel schedule. And I hope that my students who will be conducting the tutorials for you will be able to not only demonstrate the capabilities of our code, but get you started in the field of excited state dynamics through applications of the LITESOPH suite of programs. So the motivation for this toolkit comes from problems of interest in our group, but also in several other groups across the world, where nowadays the emphasis is on understanding light matter interaction in various platforms. For instance, you might want to know how the interfacial charge transfer occurs across systems, such as nanoparticle and some semiconductor. This may be relevant for photovoltaics, photocatalysis, and so on. Or there's a huge class of problems involved in biological systems where light interaction can lead to not only enzyme catalysis, but also mutations in DNA, or even repair of the DNA, and so on. And you can also look at how energy is transferred across molecules in natural systems or even artificially created assemblies. What are the details of the structure and how that governs the transport efficiency and so on. Of course, there's the class of photocatalysis, which you would be interested in order to predict or even improve selectivity of reactions by predicting the mechanism and so on. So having all these problems is our focus. It becomes important to ask what theoretical tools can be employed. Particularly, we would like to have theoretical tools that are computationally extremely efficient, because the size of these systems is ever growing. And we'd like to, at the same time, not have too much compromise on accuracy. So what sort of methods are, offer themselves up for use? Of course, the answer is at this point density functional theory, because as we know that it's rooted, or it's a nice way to map the many electron problem to one electron problems, and it is extremely computationally efficient these days. There are several codes that implement DFT in a very efficient way, and we can look at system sizes of not just a few tens of atoms, but all the way up to thousands of atoms with fast computers and efficient algorithms. So let me just start off by introducing DFT to those of you who aren't familiar with it from before, but this is not going to be a comprehensive sort of introduction. I'll just briefly motivate the idea. So the basic idea dates back to 1964 in the paper of Hornberg and Kohn. It said that there is an exact mapping possible. So before I say exact mapping, let me just say there's an interacting n-electron system, which is usually the target of our calculations. And there exists a one-to-one correspondence between external potential, the external of R, that usually decides the Hamiltonian, and the ground state single particle density or single electron density n naught of R. So of course, knowing the external potential, we know how to derive the single particle density. That's by solving the Schrodinger equation, getting the ground state wave function, and then integrating the ground state wave function over n-1 coordinates to get the density. But the Hornberg-Kohn theorem says that if you know the density, you can work back what the Hamiltonian was that generated it. And therefore, it's a new way of looking at the Schrodinger equation, a very important way too. The immediate implications are that this allows for the definition of a universal energy function, which means that you can define the energy as a functional, not a function, but a functional of the density, involving what is called a universal part, or the kinetic energy, the interactions, plus the interaction with the external potential. Now, of course, this in itself is not good enough. All this says is that there exists a functional. What becomes important is that you can minimize or this functional has a variational property. If you optimize the functional subject to the constraint that the density itself integrates to the total number of electrons, then the optimal value of the optimizing value of the density and not of R is just the ground state density, and the optimal value of the energy is then the ground state energy. So having set up these two problems, the next question, of course, is that how to make this practicable, and the answer was given by Kohn and Sham. So by identifying that if you have two different systems differing not in the number of electrons, but in the nature of the interactions, you can still ask for external potentials different in the two different systems that can still yield the same ground state density. For instance, if you have a non-interacting system and an interacting system, the interacting system external potential, you can ask for the external potential that you would have to impose on the non-interacting system that would yield the same ground state density as the interacting system. So this gives the Kohn-Sham equations, and the Hamiltonian for the independent electron system or non-interacting system is given by this expression here, where the external potential is Vs. Vs is related, of course, to the physical external potential on the interacting system, plus these factors which arise from the electron-electron interaction in the interacting system. So they appear as an effective potential that you can use for the one electron system. Note that this might remind you a lot of the Hartree-Fock equations, and indeed that similarity is there to some extent. But remember that unlike Hartree-Fock, the mapping that we just set up is an exact one, and the Kohn-Sham system is just an auxiliary system. The system of non-interacting particles, also called the Kohn-Sham system, is just an auxiliary system and allows us a way to get the ground state density, which we can then use to compute properties in the non-interacting system. A key part of the problem in DFT is identifying exact expressions for the exchange correlation functional that is computed as exact kinetic energy minus the non-interacting kinetic energy and a correction of the interactions. It's not possible right now to know what the exact form is, but you can get very reliable approximations, and that's been the sort of challenge that people have faced in the last few decades. There is the localized density approximation to this generalized gradient approximation. You have the hybrid functionals, meta-GGA, and so on. So a whole ladder of functionals available. The point is that using whatever approximation, you can develop the Kohn-Sham potential or the external potential in the non-interacting system, solve the Kohn-Sham problem, obtain the ground state density of the non-interacting system, which, of course, by construction is the same as the ground state density of the interacting system, and hence you can obtain all the properties of the interacting system. Vs of R depends on the density, so solving this equation is going to involve self-consistent field methods, and it's done often iteratively. The properties you can get as density functions if you know how they depend on the densities. A lot of the properties are known, some you have to develop, and that's also been something that theorists have worked on in the last few years, last few decades, to develop properties as a function of density. Some are non-trivial and need some work, and that is being done. Yet there are properties such as total energy, relative stability of structures, dipole moments, magnetization, equilibrium volumes, reactivity, etc., which have been calculated, predicted for several materials in almost exact agreement with experiments. And hence, DFT has proven to be hugely successful in material science for the predictive power and accuracy that it provides at not a very significant computational cost. And when I say this, I compare it to the other electronic structure methods that offer, accuracy, include a lot of the electron correlation, and work without much experimental input. So DFT is one of those success stories. Of course, it has its pitfalls, and which has also been identified. But the experts or DFT practitioners are very well aware of those and know how to navigate uh, around such problems, avoiding any application that is questionable and clearly limiting their application to, or clearly limiting their predictions to applicability areas where DFT is applicable. The thing that actually makes it successful, and if you know a little bit the story about the Nobel Prize in Chemistry awarded to density functional theory, then you would realize this, that what makes it hugely successful is the easy availability of codes and the relatively easy learning curve to master these. Nowadays, every single lab in chemistry departments across the country, you would see that people very quickly can do DFT calculations without even much introduction to the theory. And that's because the codes that are available are so easy to master, at least to be able to start running calculations and ask questions, right? And that's really the reason for success of DFT. Now, having mastered the ground state, the next question is that can we ask similar questions if a system is excited? In the sense, is there a theory that can predict or that can map non-interacting problems or interacting problems in the excited state to non-interacting problems in the excited state? Turns out that it can be done, and the basis for this comes from the Runge-Gross theorem from back in 1984, which established that just like you would be able to get single particle densities, instantaneous single particle densities from a time evolving potential, you can also obtain the external potential, time dependent external potential, uniquely within some limits from the time evolving single particle density. So this is again a one-to-one mapping that they showed can exist. And in the procedure, they also define another quantity, an exchange correlation potential, but this time a time-dependent exchange correlation potential, which is defined through derivatives of action. It's not going to the details, but we know that this term will arise because of the way we define the single particle, the mapping to the single particles. The most important here is that there's a one-to-one mapping. And what really makes this usable, practicable, is the analog of the cone-sham theory is the Van Leeuwen theorem, which says that you can obtain the same density profile in time for that you obtain for an interacting system. You can obtain it on a non-interacting system by choosing the time evolving external potential on the non-interacting system appropriately. And that gives you a time-dependent cone-sham scheme. And for us, this is the most important equation as we go ahead. We won't see it again explicitly, but that's the equation that we will work with. So you see that the psi i's are the cone-sham, time-dependent cone-sham orbitals, and they evolve under the action of a Hamiltonian, which looks like this. This is the kinetic energy term. There's the physical external potential, the same as the impacting problem, plus two potentials, which are like the mean field of the other electrons. One is the Hartree potential, the other is the exchange correlation potential, which I have referred to up here. The time-dependent densities can be obtained by summing over the cone-sham squares of the cone-sham orbitals, and so at any instant you can get the single particle densities, and the same densities also are applicable for the interacting system. Therefore, by integrating one electron equations, you are able to get many electron densities as well. Amazing. So how do we put this to use? So in practice, there are two versions of time-dependent DFT that are often used. One is in the frequency domain, or I've written here as linear response. Of course, you can do quadratic response also, but I'll deal here with the linear response. So there is linear response of frequency domain TD-DFT, where you take the time-dependent cone-sham equations and then you set up a potential that is very weak and has some frequency dependence. And this is to emulate or to simulate the action of some lasers or light fields which are occurring at some frequencies. And at small enough fields, you can develop the expression for the density response function, and solving for the poles of the response function will give you the excitation energies, and it turns out it can give you oscillator strengths, as well as it identifies the dominant particle-hole pairs. The particle-hole pairs are basically like the molecular orbitals that are involved in an excitation. Remember that in an interacting system, there are really no molecular orbitals. This is just a representation we choose for our convenience, but you can try to think of any excitation interacting system in terms of the excitations in terms of molecular orbitals, but then you'll not get one, you'll get several. So therefore, you'll have to identify which are the dominant. Some may be more, some may have contributed more than others. And those of you who've done DFT to some extent would recognize that this is just identifying the nature or the character of an excitation. For instance, if it's HOMO to LOMO, HOMO minus 1 to LOMO, etc. But this is afforded if you do linear response time-dependent DFT. You can go forward and not only compute spectra, but you can also do what are called non-adiabatic dynamics, which is a very, very important part of photochemistry. And you can use things like surface hopping to include nuclear dynamics and be able to predict, once excited, what geometries would end up in the molecule or in the material. The downside is that it requires a convergence with unoccupied states, and this is, for the most part, there are methods which obviate the unoccupied states, but then have their own issues in terms of limitations, a scope of applicability. And the other thing is that, because of this involvement of unoccupied states and several other reasons buried in the solution of the poles for response function, the method can be computationally expensive for very large systems. Remember that we are looking at large systems. Typically they could be 100 atoms or more, and the scaling can be anywhere between n squared to n cubed, which is not desirable. On the counter side, one could ask, why don't we just integrate the time-dependent Kohn-Sham equations directly? Yes, you can do this. The first people to show this, Yabana and Bush, and since then, RTT-DFT has come a long way. This is called real-time DFT or sometimes propagation DFT, where what you do is that you numerically propagate the time-dependent Kohn-Sham equations with the external potential, of course, having let's say in the molecule, this would be the ionic potential plus the externally applied laser fields, and you can get spectra. If you can propagate them, and I'll show you how this can be linked to spectra, optical spectra, by Fourier transforming time-dependent dipole moments. You can also, at one shot, just one propagation, get a broad range of excitations, whereas in linear response DFT, one has to target the excitation, so you can get a few. The calculation depends upon how many you target and so on. Right? But here in one shot, you can get a broad range of excitations. You will see that when you do the tutorial as well. You can go beyond linear response because actually what you're doing is just solving the Kohn-Sham equations. So there is no reason that these applied potentials have to be in the linear regime. You can take large fields. You can apply a variety of external fields and be able to propagate and get their response in the electronic system. So that makes this very general. The dynamics of nuclei is usually implemented through an Ehrenfest dynamics. And this differs a little bit from the surface hopping technique that is often applied in the context of linear response DFT. But it's also another way to get non-adiabatic dynamics, the excited state. The good news is that the technique is computationally efficient, and particularly if you go to larger sizes, where the scaling becomes n to n square compared to n square to n cube in the linear response. Immediately, it might seem that particle whole characters of excitations are not available immediately, are not available. But then I'll show you that you can actually have access to this if you play some tricks with the density that you get out of the simulation. Okay, what are the properties of the time-dependent exchange correlation potential? So one property that emerges is that it's got non-locality in time, so there is a history dependence. So the time-dependent exchange correlation potential at any instant, in principle, depends on all the densities attained in the past. And it's a difficult piece to keep track of. In fact, we don't have any exact formulations of this available. So what often one does is just use what is called the adiabatic approximation, where one says that the instantaneous, the exchange correlation potential at any given time t is the same as the exchange correlation, ground state exchange correlation potential one would get if I take the instantaneous density as a ground state density. So in principle, the two formulae for VXC and VXC naught don't have to be the same. Therefore, this identification here is actually an approximation. It's called the adiabatic approximation. By doing this, of course, you're ditching all time dependence, and that has consequences. And I'll show that to you in the next slide. The potentials are also non-local in space, but this is something that even the ground state exchange correlation potential has. And now it will be even more obvious, the connection, because we are actually using the ground state exchange correlation potential. Therefore, the potentials depend on densities at all points in space at a given instant, and this is a numerical problem because you have to keep track at every instant of all the dependence on all points in space. But one often gets away by using local and semi-local approximations, just like in the ground state DFT. Well, why not? We are using the ground state functional, but this does pose challenges for certain kinds of problems, and I'll mention that too. By the definition or the derivation of the theorems, there is what is called an initial state dependence. The time evolved potential depends on the initial wave function of the non-interacting as well as the interacting system. One easy way to get rid of this dependence is that you always start your propagations from the ground state, where the cone-sham orbitals have been attained. Therefore, if you know the ground state density, that's the initial density, that our Hornbook theme says that if you know that, then you know everything else about the system, including the wave function of the interacting system. You don't actually have an expression for it, but you know it. Therefore, all of it can be just set as a dependence of the initial density. So you can remove the additional dependence on interacting states. What do these things imply? What challenges do they bring to our simulations of properties? Well, the adiabatic approximation reduces the scope of the method. In fact, sometimes I'm sure a lot of people sitting in the audience are going to be disappointed because things like double excitations, excitons in solids, etc., are not described very accurately. In the field of singlet fissions, I think double excitations are very critical, but DFT would completely miss this, or to a large extent miss these. All state preparations must necessarily done from the ground state, so that the initial state dependence is removed. Now, of course, since you're using the ground state exchange correlation potentials, your bonding descriptions are just going to be as accurate as the ground state. Right? So keep those things in mind. Okay, so how do you put this to use? So one easy thing that you can do is compute the optical spectrum. Let me motivate the idea. So consider exciting a two-level system with a laser, let's say with a small intensity. Now, from our study of time-dependent perturbation theory, we know that after excitation, the system is going to end up in a superposition of the ground and the excited state. If you then turn off the laser, the instant, or even if you don't, the instantaneous dipole moment is going to be given by this expression where you have the direct terms and then the interference terms. See, the direct terms will often, so if you turn off the laser, then these coefficients will have their values at the last moment when the laser was on. So these would actually be constant beyond a point. And these two terms would have no time dependence. However, there would be a time dependence that would come from the rest of the term, and that is the superposition part. And what will happen is that the superposition will then lead to oscillations that are going to depend upon the energy difference between the two levels. So in principle, all you need to do is, you can take a Fourier transform of the time-dependent dipole moment, and you will get peaks corresponding to all pairs of states that are connected by the laser. Right? So that's the idea. That's what we're going to do, and that can be, the Fourier transform can be related to the strength function. The strength function is given by this expression. You take the imaginary part of the Fourier transform of the dipole moment, multiplied by these two factors, where E is the strength of the electric field applied, and you get the strength function. This is basically the spectrum. And in practice, the electric field polarization that you take is along one of the axes. So this is exactly like you would do it from a textbook, right? So if you want to compute the total polarization of, let's say, a molecule in the gas phase, which is usually averaged over all directions, then you'll have to run 3 different simulations, one along X, one along Y and Z, and then take the average spectrum to get the the total strength function, and then compare that to experiment. So the frequency dependent induced dipole moment is then just this expression. So in this case, I've taken the X polarized laser, and this del N is the induced density, frequency dependent induced density. So let me show you an example of this that we have done recently. So we've looked at size-dependent electronic and optical properties of transition metal dichalcogenide flakes. These are triangular flakes, and if you increase the size, these are various MOSE2, T2, WSE2, and WS2. So if you increase the size, there is a peak that comes around 2 eV for small flakes, and that shifts, red shifts as you increase the size. The red shift behavior has been associated with plasmonic behavior in the past, and a few slides down, I'll show you that the system does have plasmons. But you can actually calculate the spectrum, and some of these, the largest system are, almost 100 atoms or so, and we can calculate them with very easily. In fact, these calculations, the largest ones were done on Param Shivai, which is, I think, where one of the params is where you'll be running your calculations, and you'll see that it's actually not so bad. You can run these calculations in a reasonable amount of time. Imagine doing all of this using linear response. There you would have a lot of trouble. I mean, in the time. And also, look at the. I've only given you a 5 EV window, but the simulation that we've done, you can get up to 10, 20 EV spectrum. All right. So let me just summarize the codes that are available with our real-time 3D DFT. This is not an exhaustive look. Turns out this is an evolving list. Some typical Gaussian basis codes are NWKM, Turbomol, Gaussian. I don't know if Gaussian, maybe Gaussian 16 has it. Yeah, and then mol GW. These codes now have real-time 3D DFT implemented. Numerical atomic orbitals are as basis. These are very, very interesting because you get the benefit of localized basis as well as the computation efficiency coming from real space grids. These are used in codes like siesta. A lot of people who are working on transport phenomena would be familiar with siesta. GPAW, people working on extended systems would have used GPAW, which basically uses projector augmented wave and has different modes. FHI AIMS also now has an implementation. There are codes which use real space grids to represent densities and wave functions. And Octopus is one of the older codes that had implemented real-time 3D DFT. And the coding in real space grids is actually very, very straightforward in terms of formula translation. But if you want to make things efficient, it takes a little bit of work. But domain parallelization offers a great way to speed up the execution of jobs in this code. Similarly, GPAW has both an NAO as well as finite difference implementation. It also is a plainwave, basis set calculation platform, but I'm not sure if real-time TDFT is implemented. That only NAO and real space have. And then there's PARSIC. There are plane wave or LAPW and this hybrid plane wave, Gaussian plus plane wave sort of codes, which include ELK, ELK, exciting, CP2K, and QBox. However, given all these codes, what I have found is that there are some general issues. A lot of these codes have efficient implementations, but from a user perspective, their scope is limited because they don't offer too much in terms of post-processing tools, right? And sometimes the thing that you need the most is not implemented. So you have to switch codes. But with every code switch, you have to learn the code and you have to, learn to make it efficient and so on. So there are way too many basis sets that you'll have to pick up and input files and technologies and so on, which makes the learning curve a little too steep for beginners. And therefore, it was desirable for us, at least a few years ago, that we have a common platform where we can ask questions. We know the physics, so we just want to be able to ask questions and not worry about the implementation, the backend, right? So we devised an idea to come up with a platform to do excited state dynamics in particular. And this toolkit is aimed at being code agnostic. So you can ask questions that are very general and the backend will implement it in whichever is the best code available. You also have the choice of picking the code. And this is called LITESOPH. And it's a comprehensive toolkit to launch, monitor, manage, and analyze large-scale simulations. It was, when developed, it was aimed at the HPC environment. So obviously there is going to be a part that really is able to launch jobs, manage, and analyze simulations. It's designed to solve the needs of computational researchers, particularly in this country, who are interested in several of those problems that we were interested in. And the features that we have so far, which some of this we will test, the absorption spectrum calculation, cone sham decomposition, molecular orbital population tracking. You can do a laser-based simulation. Some of the things that are coming up are non-adiabatic dynamics. Both are infest and surface hopping are yet to be implemented. Some of them are, but not linked to the code. Right? Effective spin-orbit interaction is something that is developed in our group, but it has not yet been attached to the LITESOPH toolkit. Then we are also trying to include, performing RT-TDFT with QMM methods to ensure that we can scale up to large sizes where the quantum area, quantum region of the problems, the focus, and the rest of it is supporting, but gives you the background, the environment that you want to work in. And analysis of, nuclear dynamics is something that's also coming. This is done in collaboration with my colleague Sebastian Booster, because Sebastian was interested a lot in energy transfer problems, and we spoke and we felt like there's a lot of common interest, and we can come up with a platform which can address questions that his group also wants to ask. And the project was funded by the Ministry of Electronic Information and Technology under the National Supercomputing Mission Initiative, in fact, under the NSM MSCC Material Science and Computational Chemistry program, which is actually conducting this workshop. Okay, so very quickly, the layout of LITESOPH. The LITESOPH was built as a layer integrated tool. The bottommost layer are the engines. So we have TDFT codes like NWChem, GPON, Octopus. You can see that we have deliberately chosen open source codes. Our code itself is open source and available to all. So we want to make sure that going ahead, we have open source codes under the hood. Of course, we allow you to integrate any code that you want. In fact, one of the main ideas was that it should be user-friendly as well as developer-friendly. So there are a lot of nice templates and you can develop interfaces on your own. There is an engine manager layer, which basically, once given input, it decides what kind of engines to use and so on. Task manager, depending on what you want, it manages all the input and output for every task. There is a workflow mode, which is managed by the workflow manager. So entire set of tasks that can be run to attain a certain goal. And then there is the project manager and the LITESOPH manager and the GUI. The GUI front end is what you will see. This is basically the workflow that you would encounter. More on this, hopefully my students can tell you a little bit more. Some of the features that have been implemented, so some of you will probably do these first few, and you can, so this is in the workflow mode, where you have a specific property and there's a set of tasks that will pop up. You will go through one by one. There are advanced usages and like particle hole character using Conshan decomposition. I'll maybe quickly show you one. So here's an example of that. So what you can do is you can actually get the single particle density matrix and you can use that to compute the Conshan decomposition in the system. You can calculate what is called a transition contribution map, which tells you at any given energies, of the occupied and non-occupied, how much is the contribution to the strength function. It's a very nice tool because I'll skip this. So it's a very nice tool because it tells you, basically, it brings back the particle hole identification that was available in linear response, very similar to what is done in linear response, but you get this from time dependent calculations. So one of the key ingredients is the transition dipole matrices, which basically decides how strong the contribution is. There's a Fourier transform of the density matrix, which is computed on the fly or even after the simulation is done, which gives you the Conshan decomposed strength function. So you can use this to identify also CIS-like expansion coefficients, which right now are not used in LITESOPH, but will be used in the future. And you can obtain the transition contribution map. So here's an example. If you take a triangular flake of MOSE2 and you look at the transition contribution map, you see these spots appearing below the resonance energy line. It refers to collective excitation. In fact, if you look at the induced charge density here, it clearly shows that you have dipole moment or like a dipole-like modes that appear on the edges. So these are what are called edge plasmons. So we predicted edge plasmon modes on these flakes, and it turns out that you can do that. Okay, the other stuff I may not necessarily have time to go through, so but the tutorials should walk you through this. And what I will do is that I will just maybe introduce the team to you. So that LITESOPH is been implemented by a lot of students in the group. It's completely student driven. These are the two people who are going to introduce you to LITESOPH through your tutorials. And with that, let me just acknowledge the funding and thank you all for your attention.
Thank you, Professor Srinivasan Padradhan. So if you have any question, the developer teams are available, member of developer teams are available on this forum. You can ask. So if you do not have any question, let us move to the next session of login onto the system. So my team is here to assist you for login. So we have already shared the login credential with you in the Excel sheet. Kindly try to log in on the Kamrupa system. So if you have any issues, you don't know how to log in, kindly raise your hands. So Ashish is sharing his screen and he is logging in the same way you log in if you have Windows or the Linux system. So he is logging through Windows system. So to avoid any delays in the hands-on session, any kind of login issues, we are having just 15 minutes of this exercise. We'll do this.
Hello everyone. I'm going to log into Param Kamrupa system from mobile extra, and I will be sharing my screen, so you can go through with that. So from here, I'm going here. You can click on Param uh, sessions, and then you go to SSH. Here you can type Param Kamrupa dot iitg dot ac dot in. Then you can specify the username that has been given to you, and then you can choose any username which have been provided to, and then you can enter the port 4422. After this, you can go here and click OK. After this, it will ask you the captcha. You have to enter the captcha VZ U Z D B A B. Enter. Then it will ask your password. So in my case, I have logged in from MSCC01. So I will do that. MSCC01, and then I will enter. After entering, I have logged it into the Param Kamrupa system via 01 user MSCC01. After this, I will do MLAV. So you can see all the modules that will be present here. It will take some time to open the modules. Can also see our GUI. It's here, MFCC LITESOPH. You can load in. And then you can open the GUI. Will take some time to open because it's GUI and we are opening it through the cluster. So here is our LITESOPH GUI, and that's it. You can go ahead and cross it. And now
Those who are having Windows system, are you able to log in? Just type yes in the chat window. If you are able to log in, please type yes in the chat window. Anubha is able to log in. Ashish will show you how to log in through the Linux system as well. Aryan Chaudhary unable to log in. It says access denied. Okay. Yeah. Aryan Chaudhary ji, have you downloaded this AnyDesk? Yes. So you can start your AnyDesk and share your number. My colleague will help you to with the login. Then you can write it here. You can share in the chat window itself, Aryan. Jai Prakash, you are okay. Unable to start LITESOPH GUI. Okay. Let us fix this in Chaudhary sir issues, and then we will look into Jai Prakash ji and Tanmay issue. Okay. So if you have also have this AnyDesk, start and share the number. Jai Prakash ji, can you start the AnyDesk and share the ID in the chat window? My colleague will connect. किनका? AnyDesk से कर.
Hello. Hello, Aryan, you are logged in. You can check your system.
Jay Prakash, can you recheck your this ID, AnyDesk ID? You're not able to connect. Aryan Chaudhary ji, are you able to log in now?
Hello. Hello, Tanmoy.
Yes, yes.
We need some permission from your side. Please check your AnyDesk application once.
Yeah, I have given there is some request came.
From my side, it is showing could not start the session, missing screens capture permission on the remote side.
Full access.
Still, it is showing the same.
Okay.
Once you try sharing your screen, we will try solving it here.
Is it now okay? Okay, maybe I can then share my screen.
Yes, as once you share your screen, we will look into it.
Hello. Hello. Jayaprakash, where are you logged in from system? Hello.
Yes, sir.
Yes. Where are you logging from your system? You are using
I'm using Linux, sir.
you are using Linux. Okay.
Yes.
So you have AnyDesk installed on your system?
Yes, I have AnyDesk installed. Your address is 132.344.170. That is the same number I have sent. Your desktop
Yes,
can be
I'm,
accessed with this address.
but I cannot access your like
Okay. I will check it
can
again,
you
sir.
okay no can you enter the command in the chat window which you are typing to log in
Sir,
in the
I
Linux
have
system?
already logged in. I have already
Yes.
loaded that. Yes, sir. I have already loaded the module, but
Okay.
when I try to open the GUI, it is not opening. I
Oh,
have given
so I
the error
think
message
you have
completely.
to
Error message in
yes.
the
So
messages, it is there.
yes, okay. So you have to like SSH X. I will send you the command, then you
Yes, sir.
can log in from there.
Yes, sir.
Okay. Hello, hello. Jayaprakash, sir, you can use this command uh,
Yes,
to
sir. Yes.
log in into your uh, Linux system.
Yes, sir.
Then you type in the command and it will open the GUI. You
Yes, sir.
have to add -X.
Sir, can you send that code again?
We have shared the command. You just need to add that -X. You just look into the command in the chat section. SSH -X. We have sent it.
Okay, sir.
Please check this chat section.
Yes.
Jayaprakash.
Tanmay can you share your screen on this meeting?
Sir, I just left the meeting and I joined
Actually,
again. I got reconnected. Can you share
the
that code once
private
again?
settings
Once
has
again.
some problem on my side. So
Yes, yes. Sir. We just yeah.
Jayaprakash, are you
Hello.
able to see the GUI?
Now we have shared the command once again. Please check it once.
Tanmay ji, can you share your screen, please? Those who are using Linux-based system, we are sharing the details how to log in using the Linux system on Param Kamrupa system. And kindly see the things. And if you are not able to log in or not able to view this LITESOPH GUI, let us know.
Children.
Hello everyone. I will try to demonstrate how to log into Linux system and open the GUI. So you can SSH -X. If you want to open the GUI, you have to add -X and then you can. So I will be taking the same user mscc01 @param rupa.iitg.ac.in and enter -p4422. Then it will ask you the captcha DSYVPSJT, enter MSCC01, then enter. Now you are logged in into the system, and after this you have to ml load MSCC LITESOPH. After this you have to and it will display you the GUI. It will also take some time. Here is the Linux GUI. It will open in your system. It will be fine. So here it is, and then you can go ahead and cross it. After this, so if anyone else is having any problem, they can tell us in the chat section. We will try to solve the problem.
Hello. Hello, Tanmay. Your issue from your side, is it solved, or do we need to attend it?
It's solved, but is some issue from the security and privacy settings in this in my system. So,
Okay. Are you using MacBook or something?
yeah, I am in Mac actually.
Okay. So,
Maybe I think you can continue. I need to solve it in another way. So I just
okay.
go through what you have done. Then maybe later I will try, and if I have some issue, I will tell you.
Okay. Sure. You can use our discussion forum for that. You can just
Yeah.
post your any queries. Thank you.
Thank you.
If you are able to log in and able to open this GUI, we'll be sharing one command where you just after login put this command onto the terminal. You will be able to download the input test data set which is required during the hands-on session. Those who are done with this, they can leave the meeting. We will be assembling back at 2 o'clock with the demo of LITESOPH following by the hands-on session. Sharp 2 o'clock, we'll be starting the demo session. Thank you, everyone. I hope you are able to log in and download the input data set. We'll be assembling back at 2 o'clock.